In this experiment, we'll look at the basics of signal propagation in electrical networks. Among other things, this enabled us to understand the propagation of excitation in nerve cells. The simplest network consists of a voltage source and a simple conductor with a resistor. Any number of resistors can be connected either in parallel or in series, thus changing the voltages and currents at different locations in the network. In this experiment, we will first look at simple circuits to understand how voltage drops across a resistor. We then connect several resistors in parallel and in series to simulate a simple model of a nerve fiber. For this experiment, there is a kit of simple network elements, simple conductors and resistors of different values. These can be combined with each other as desired. The voltage for the entire network can be set on the power supply unit. We use multimeters to measure the current and voltage. For the first experiment, we build an unloaded voltage divider by connecting two resistors in series. We connect the cables from the multimeter before and after a resistor to read which voltage is dropping. This voltage measurement is performed for 5 different values of the input voltage, one for 10 kilo-ohm and one for 100 ohm resistors. We now connect another resistor in parallel to the second resistor. This results in a loaded voltage divider, and we measure the voltage that drops across it. The input voltage remains the same at 5 volts, but we repeat the measurement for different resistance values. By determining the relationship between the voltage drop and the input voltage, we can now confirm Ohm's law and Kirchhoff's rules. In the second experiment, we again have a parallel connection of resistors. Each resistor is identical with 390 ohms. Each resistor simulates an open ion channel in a membrane. We start with one resistor and increase to 10. We can measure the voltage drop across the resistor network at any resistor since it is a parallel connection. The current is measured by a multimeter connected in series at the end of the network. For the circuit with 10 parallel resistors, we now vary the output voltage of the power supply in 1 volt steps. For each step, we measure the voltage drop across the resistors and the current. By plotting current to voltage, we obtain the so-called IV characteristic. In the third experiment, we combine resistors in series and parallel. There are 8 links, each with a resistor of 390 ohm connected in parallel and a resistor of 100 ohm in series. Here, the resistors connected in parallel are analogous to the membrane resistors of a nerve cell. The resistors connected in series represent the internal resistance in the intracellular space of the nerve cell. In total, the circuit thus simulates a long, thin nerve cell. We set the output voltage of the power supply unit to maximum. This corresponds to a depolarization of the nerve fiber. We now measure the voltage that drops across each of the membrane resistors to illustrate how the depolarization decreases along the nerve cell. For the simulation of a thick nerve fiber, the internal resistors are replaced with 50 ohm. We again measure the voltages across the membrane resistors. We now replace the internal resistors with the original 100 ohm and replace the membrane resistor with 10 kilo ohm. With this, we simulate a myelinated nerve fiber. Again, we measure the voltages across the membrane resistors. For each of the 3 different simulations of nerve fibers, plot the measured voltage at the nth resistor against the number n, and thus determine the longitudinal constant. This is a measure of how far the depolarization is transmitted in a nerve cell. Altogether, this experiment allows us to understand the basics of simple electronic networks. The combination of parallel and series resistors for the simulation of the voltage drop within a nerve cell is of course greatly simplified, but it illustrates the principle of stimulus conduction and shows what it depends on how far a stimulus comes until it has to be amplified again.